So for algebraic topology, we need a bit of general theory of abelian groups. So that's what we'll start to develop in this video. Okay, so the first thing is we'll always use additive notation. So our group operation is written as a plus b. The neutral element is 0, and the inverse minus a for a. Okay. So you know, the abelian group, say integers under addition, is a basic example of that. So given abelian groups a and b, we can consider their product. It's traditional to write this with a direct sum symbol in this situation. So this is a set of pairs a comma b with a and b and b. So that forms an abelian group in an obvious way. And most basic examples. Well, you've got just the integers, and then more generally you can have z to the n as vectors of length n with integer entries, so that's an abelian group under addition. And then also things like z mod d for positive integers d. So so z mod d here is well, a couple of different ways to think about it. You can think about it as just being the set 0 up to d minus 1. The group operation is addition mod d. And then this is more or less the same thing as the quotient group z mod dz. So that's sort of remember this is a quotient group, so the elements are cosets I plus dz for I and z. Okay. And we need to have think about various homomorphisms between abelian groups. One kind of key thing to think about is homomorphisms between groups of this form z mod dz. So let's just make this a little lemma here. So let's let n, m, k be integers. N and m are going to be strictly positive. And we're going to assume that nk is divisible by n. Okay. Then there's a well-defined homomorphism. Which I'll call phi from z mod n to z mod m. Given by phi of I plus nz is going to be ki plus mz. Okay, so the main point is just to check that this definition here is well defined. Yeah, so suppose that I plus nz is the same as I prime plus nz. So I prime is, let's say, I plus nu for some u. Then if we look at ki prime, well, that's going to be ki plus knu, and kn is divisible by m. So that means that ki prime plus is the same as, so that's therefore ki prime plus mz is the same as ki plus mz. So this definition is well defined. if I represent the same coset in two different ways, I still get the same answer on the right hand side. And then, so given this, I won't say anymore, it's easy to check that phi is a homomorphism. Okay, so next key thing that we need is the so-called Chinese remainder theorem. Which says that if n and m are coprime, then the group Z mod nm is isomorphic to Z mod n direct sum Z mod n. Okay, so this definitely needs n and m to be coprime. We'll see examples to see why that is a bit later, but at the moment let's just prove the positive statement. So n and m coprime means exist A comma B with a n plus bm is equal to 1. So let's define a map phi from Z mod nm to Z mod n plus Z mod m. In this direction, there's really not really much to prove. By phi of I plus nmz is I plus nz, I plus mz. So it's kind of more or less obvious that this is well defined, or you could see it as being an application of the lemma we proved a moment ago if you want, or you can just see it directly. Okay, so that's a homomorphism in the first direction. Okay, now let's define a map alpha from Z mod n to Z mod nm. Alpha of j plus nz. Okay, so this is going to be bmj plus nmz. So again, we need to check that this is a well-defined rule. That's again, this is if you like an application of the lemma we had a moment ago, or you can just see directly if we change j to any other representative of j, it differs by a multiple of n. And then so you're multiplying it by m here, so that gives you something divisible by nm, so you don't change the coset on the right hand side. Do the same beta of k plus mz is going to be ank plus nmz. Again, if I change my k by a multiple of m, then the ank gets changed by a multiple of nm, which doesn't make a difference. So that's well defined. And now we're going to define psi. So then I just combine these two things in an obvious way. So alpha of j plus nz plus beta of k plus mz. Okay, so that just going back to the definition here, that's bmj plus ank plus nmz. Okay, so now we've got well-defined homomorphisms in both directions. And we need to, or to claim that their composites both way arounds are the identity. Okay. Okay, so one way around, let's look at psi of phi of I plus nmz. Okay, so that's psi, just filling in the definition of phi, that's I plus nmz. So I plus nz, I plus mz. And then just filling in this definition of psi here, this is bmi plus ani, because in this case your I and your j are both, your j and your k are both equal to I. Okay, but that's an plus bm I plus nmz. But we started, this was this a and it's b which came from up here, so an plus bm, that's equal to 1. So that's I plus nmz. So that means that psi composed with phi is the identity map from z mod nm to itself. So now let's think about suppose we do phi of psi of a pair like this, j plus nz, k plus mz. That's phi of bmj plus ank plus nmz. Okay, and so here, so if we look at the definition of phi, so we just reduce mod n. Okay, so here you get bmj, and so we could say bmj plus ank plus nz, but the ank of course doesn't make a difference. The ank is already in nz, so we can just leave that out. And then in the second component, you've got this thing plus mz, but this term here, that's already in mz, so that doesn't make a difference. So we can just remember the ank plus mz. Okay, now bmj, so bm is 1 minus an. Okay, so that's j minus anj plus nz. And so similarly, an is 1 minus bm, so that's k minus bm plus mz. But again, here we're working modulo n, so the anj doesn't make a difference. Here we're working modulo m, so the bm doesn't make a difference. So that's j plus nz, k plus mz. So phi composed with psi is the identity on this direct product. Okay, so that's the Chinese remainder theorem. If n and m are co-prime, then z mod nm is the same as z mod n plus z mod m. But it doesn't work if n and m are not co-prime. Let's look at the most basic case. If you look at z mod 4 is not isomorphic to z mod 2 plus z mod 2. Here, this is 0, 1, 2, 3, and this is sort of like 0, 0, 0, 1, 1, 0, 1, 1 under multiplication, addition mod 2. So here the elements 1 and 3 have order 4, and here all elements have order 1 or 2. So these two groups are not isomorphic, and similarly, z mod n m is not going to be isomorphic to z mod n plus z mod m if n and m not co-prime. You could take it as an exercise to show that this really is an if and only if thing. Okay, so But let's also, we can extend the proposition by induction. So if if we look at a group like Z mod M1, M2 up to MR, then the splits as the direct sum of the constituent things, provided we've got this condition here that the GCD of Mi and Mj is 1 for all I not equal to j. In other words, the numbers M1 up to MR are pairwise co-prime. So in particular, if we've got a number n, then we can try and factorize it. We've got a positive integer n, then we factorize it as a product of powers of primes, and then of course each of these individual factors is they're all co-prime, so you find that Z mod n is isomorphic to Z mod p to p1 to the v1 plus up to Z mod pr to the vr. That's what we get from the Chinese remainder theorem. And that's all we'll say for this first video.